So continuing on the theme of gravity for this session, I'm going to be talking about radiation pressure and quantum noise in gravitational wave detectors and related systems. So an overview of what we're going to talk about today. First, I'll give you an introduction to gravitational wave detectors and the origins of the quantum noise that we see in these systems. Then I'm going to focus in on the effects of radiation pressure and discuss how these classical optical forces help us approach the quantum regime in systems like these, and also discuss some experiments that we've carried out in our lab to demonstrate these forces. Then I'll discuss the work that's currently underway in our lab to uncover the quantum noise effects of radiation pressure, and then we'll have a conclusion. So what is a gravitational wave? Well, the concept has been with us for a long time, dating back to Einstein's general relativity. Since then, we've thought of gravitational waves as propagating ripples in space-time. What do these ripples do? They stretch and squeeze the space transverse to the direction in which they're propagating. And it's important to remember that the effect of a gravitational wave that we see is dependent on the length of baseline over which you're measuring. So it's a strain, a change in length divided by length. And what can make gravitational waves? These are, just as electromagnetic radiation is generated by accelerating charges, gravitational radiation can be made by accelerating masses. And the types of systems that can give us a signal big enough that we could hope to detect are astrophysical systems. Things like cosmic explosions, which could be supernovae or the Big Bang, collapsed stellar remnants that are orbiting each other and inspiraling and coalescing, or mountains of stuff that are stuck to the crust of neutron stars spinning around. So, since the theme of this session is big ideas, I wanted to give you some motivation for why we detect gravitational waves in the biggest system that I could think of, which is, this is the whole universe on one view graph. And the only message I want you to take from this view graph is, if you ask yourself, what do we know about the universe and how do we know it? Almost everything that we know comes from looking at light, electromagnetic radiation. And in particular, our knowledge of the very early universe comes to us, a lot has come to us from the satellite WMAP, which is looking at the oldest electromagnetic radiation in the universe, the cosmic microwave background, which dates to 400,000 years after the Big Bang. So why can't we look back any further than that with light? Because the very early universe was opaque to light. So if we want to get a signal about what was going on before a direct signal from before that epoch, we need to have a carrier that is weakly interacting with the stuff that was in the matter that was in the universe at that time, which an example of that is gravitational waves. So that's one reason why we want to detect them. How can we look for them? Well, we want to use our most sensitive toolkit for monitoring displacements to look for these changes in length, and that's laser interferometry. So like other optomechanical systems that you'll hear talked about in this workshop, we're relying on lasers and mirrors and mechanical structures for supporting our mirrors. What makes this system a gravitational wave detector, what's special about it are three things. One, we need to have a very long baseline over which to measure our changes in length, so we have kilometer scale cavities. Two, we want our mirrors to respond as free particles to the gravitational wave as it's passing by some frequency. So we suspend them with a low resonant frequency. The mechanical resonances in our system are low frequency, typically on the order of 1 hertz. And finally, it seems like there's two of everything in this picture. There's two arms, two cavities. And the main reason that we do that is for rejection of laser noise. So we are measuring a signal that's going to show up in the differential mode of the two cavities. And all the frequency and intensity noise on the laser is going into the common mode of the two cavities. So we get a good rejection of those two. Now what about the quantum noise in this system? So here we're looking at the quantum noises in initial LIGO, which has recently wrapped up its data taking. And the cyan trace here shows the quantum noise. And this quantum noise comes from two pieces, the shot noise, which comes about because we're only using a finite number of photons, and there's some statistics of counting those photons. There's a finite amount of information you can get out from them. And at low frequencies, what takes over is radiation pressure noise. Because we have a finite number of photons, and it's not a constant number, it's a fluctuating number due to quantum mechanics, there's a fluctuating force coming from the momentum that those photons impart to the mirrors. And so this creates a limit at lower frequencies. And the point where these two contributions are balanced, we refer to as the standard quantum limit. And that's actually a function of of power. At different input powers, you can get have this kind of quantum limit occur at different frequencies, and you can get more and more sensitive with more power. So why don't we see the radiation pressure noise in initial LIGO? It's because we have seismic noise at very low frequency and some thermal noise and other things out here. So the only quantum noise we're seeing in initial LIGO is the shot noise. In advanced LIGO, on the other hand, we would like to increase the laser power in order to drive the shot noise down. So that means we're making a stronger measurement of our system. And the price we have to pay for that is that there's going to be more backaction, more quantum noise coming up at lower frequencies. And we're also going to do some things with seismic isolation and suspensions to try and get these other noises out of the way. And we do expect in advanced LIGO to be limited by quantum noise throughout most of the band where we're sensitive. Where does the quantum noise really come from in these systems? It comes from the light that we're using to measure. So there's a Heisenberg uncertainty relation for light, which is relating the amplitude and phase quadratures, telling us that the product of the uncertainty in those two has to exceed some level. And in classical states or vacuum states or coherent states, the contribution of the amplitude and phase is equal to that product. But we can also use squeeze states. Since the measurement we're trying to make, the signal all tends to be in one quadrature, we can reduce the noise in that quadrature at the expense of increasing it in the other. So that's what squeeze states are good for. Now, dealing with a Michelson interferometer, we have to remember that the measurement we're making is rejecting whatever noise is on the light coming in the laser port. It's only the vacuum state that leaks into the open port of the interferometer that matters here. So we send vacuum state in, it mixes with the light on the beam splitter, enters the interferometer, comes back out, and we then see that noise on top of our signal. We can use squeeze state in the following way. If instead of letting the vacuum enter, we put a squeezer here to squeeze, say, the phase quadrature where we expect to measure our signal, then we can hope for realistically something like a 6 dB improvement with today's squeezing technology in terms of the level of the shot noise. Now, the price we're paying for this is that the radiation pressure noise, which depends on the amplitude quadrature, that's what we've made worse by squeezing, is going to go up. So after many years of development, squeezing is actually now being demonstrated for use in gravitational wave detectors. And this photo is showing a squeezer that's been installed at the geodetector in Germany, and a similar test is now underway at the LIGO Hanford interferometer. So squeeze vacuum is being injected into the dark port of these interferometers to reduce the shot noise by up to 6 dB. Now, what about the radiation pressure? So radiation pressure was an insignificant effect in the first generation of gravitational wave detectors. But it's about to become critical, both to the classical dynamics of these systems and to the noise. So, as I've told you, raising the laser power is going to reduce the shot noise. That's why we're doing that. It strengthens the coupling of the light to the mirrors. And now the classical dynamics of these systems can be dominated by the radiation pressure forces. And there's two components to that force. There's a restoring force, which we're going to use to do optical trapping of these mirrors, and a damping force, which we can use to do optical cooling. The quantum fluctuations of the light that we're sending in can act back on the mirror. That's making the radiation pressure noise. And as a consequence of this, both quadratures of light become correlated with the mirror's motion. One is driving it and the other is sensing it. And this can lead to squeezing and entanglement of the light that exits the interferometer. And where do optical forces come from? Here I'm showing you the intracavity power on this curve, which is also the radiation pressure force as a function of the mirror displacement. At the very peak here, you have maximized it, but as soon as you detune in either direction, it becomes linearly dependent on where the mirror is. And that creates either a restoring force or an anti-restoring force, depending on which side of the resonance you parked yourself on. Now there's also an effect, which I'm representing with these small ellipses, representing the fact that the light in the cavity doesn't actually follow the mirror motion instantaneously. There's some time delay as it builds up and decays away. And so this creates a damping force or an anti-damping force. And the one unfortunate aspect of this is that no matter which side of the resonance you choose to park yourself on, being detuned either way will introduce a force that tends to destabilize the system, whether it's the anti-restoring force or the anti-damping force. So if all optical forces are dominant, either case is unstable. Now, why are we interested in these optical forces? Well, one thing we might like to do for quantum optomechanics is to put our mechanical system into a well-defined quantum state. But it always starts off being coupled to a finite temperature environment. So it's coupled through some damping rate, gamma sub m. And from the fluctuation dissipation theorem, we get a fluctuating force on our mirror that's kicking it around, depending on the environmental temperature. An optical damping force lets us couple our mechanical system to the nearly zero temperature optical field. Can this let us achieve ground state cooling? Well, in order to do that, we need to minimize the occupation number, which is dependent on sort of the scale of the thermal energy to the quantum energy. And this means it's a very challenging regime for gravitational wave detectors because we're always starting from an environment at room temperature. We're using relatively low resonant frequencies of our mirrors, and so the thermal scale is much bigger than the quantum scale. And to get to the ground state, you would need to put your system into an effective temperature of 50 picokelvin. So you need to do an enormous amount of cold damping to get there from room temperature. So what makes forces cold, actually? When are optical damping forces cold? Well, the noise limit to the optical damping force is due to vacuum noise that leaks into the cavity, which equivalently is information about the mirror state leaking out. And in order to keep the rate of that leakage small, you need to have a low bandwidth cavity, sometimes referred to as a good cavity, where the damping rate of the cavity is much lower than the resonant frequency of the mechanics. If you're in the opposite regime, as gravitational wave detectors and related systems are, we have very low frequency mechanics. We can't make a cavity that's that good. We need to do something else. Since the light that's leaving the cavity is carrying information about what the system is doing, what we want to do is sense the mirror displacement using that light and then feed it back. And we can make a cold feedback force, where the noise limit there will be due to whatever noise you have on your readout. Now, I've told you about damping forces. I want to also mention restoring forces, because these will be important. This is actually going to be the trick that lets us approach the ground state in systems where the natural resonant frequencies are low, because they have two very beneficial effects. They increase the effective quality factor of the system. If you can add a restoring force without adding damping, you can make the Q bigger, and also without adding noise, as optical forces can do. And secondly, you're just increasing the quantum energy scale of the system by raising the resonant frequency. So now you don't need the 50 picokelvin anymore. You could be 100 times that, which is still challenging, but not as ridiculous. So since radiation pressure is going to be important for gravitational wave detectors in the future, we've built a testbed to do some tabletop scale experiments with these forces. So it's actually constructed sort of on the same lines of a gravitational wave detector, minus the kilometer scale cavity lengths. And here we've also introduced using much smaller mirrors, gram scale mirrors, as compared to the kilogram scale mirrors that are used in gravitational wave detectors, to make the system a lot more susceptible to radiation pressure. The other thing that we sometimes do is to inject two different colors of light into different polarizations. And this allows us to generate two sets of optical forces at the same time. Here's a picture of how it looks inside the vacuum chamber. So we can send in up to 10 watts of pre-stabilized laser light. It enters the two arms of the interferometer here and here. The mirrors are only 1 meter apart, not 4 kilometers. And the cavities have a finesse of about 8,000, which builds up to a circulating power of on the order of 10 kilowatts, which is actually comparable to what you see inside the cavities of the initial phase of gravitational wave detectors. And here's a photo of one of those 1 gram mirrors with the cavities locked, and so it's bearing the brunt of all that radiation pressure. And from outside the vacuum chamber, this is how it looks. So we have a vacuum envelope with about the same volume as my apartment. We rely on several stages internally of vibration isolation, which are passive, and also an active external vibration isolation system, which lets us work in this urban environment. And then the 10-watt stabilized laser lives next door. Now, focusing in on the mini-mirror suspension, this is our latest and greatest technology for mini-mirror suspending. We've been through a couple generations of that. So currently we're using glass fibers to suspend our mirror, and they taper to 200 microns diameter here in the center. We do that in order to make sure that all the bending in the system is occurring away from the attachment points in the most pristine part of the fiber. So doing that has let us measure Qs for the lowest frequency, the 10 hertz mode of this system, in excess of 1 million, which means if you give it a good kick, it will ring for up to a day. I also want to point out here that as a result of tapering, there's a part down by the mirror that's untapered that we refer to as the ear, and what that's supposed to do is prevent any bending from happening here, and that's going to become important later in the talk, so I want to make sure you know that. This, yes, that's the ear. It's the same as the fiber. Yeah. So this technology for making these shaped fibers is also going to be used in advanced LIGO, so that's why we had access to it. So to make use of the strong radiation pressure forces in the system, we have demonstrated optical trapping and cooling of one of our mirrors. So this was all done using just a single cavity. We made a very stiff optical spring force, which was able to shift the resonance from the suspension we started out at was around 172 hertz, and we pushed it out to as much as 5 kilohertz. So that's extremely stiff. It's the same kind of stiffness that you would get if you were to replace the cavity mode with a diamond rod of the same dimensions. And the DC radiation pressure force in the system amounts to about 1% of the gravitational force. So a spring that stiff would not be stable on its own, so we can stabilize it either using feedback, or in this case we used 2 different colors of light, and we made a double optical spring out of those. So the idea behind that is that you can make a spring where the restoring force coming from one field is very strong, and using the other color of light, you can make a strong damping force that's detuned the other way, and the combination of those two can be stable if you choose the parameters correctly. And that's what's shown in this purple trace here. The decrease in phase as you go through the resonance indicates this is stable. So then we were able to see that the system was quite cold. We had a cooling factor which was augmented by having shifted the resonance out to a couple kilohertz from where we started, but we were limited in the end by laser noise in this system, because we only had a single cavity here. To try and do better, also with a single cavity, we just made a shorter cavity, so the light laser noise was less important. And then we went to electronic feedback of our displacement to do our damping instead of the optical damping force, and this let us damp and stabilize the optical spring, and it let us do about a factor of 100 better.
So,
yeah.
Compared to the previous noise spectrum you showed us, this one looks a little uglier. Why is that?
Well, let's see.
Those look like nice Florentians, those less nice.
Less nice.
So, it's a vague notion of niceness.
So do you mean that they look less like the Platonic form of a Lorentzian?
Yeah, right.
Or are you talking about the fact they're kind of ragged in some places?
I would have considered both of those in the same thing.
Okay. Well, I think one reason why they get more ragged is because just the displacement scale has gotten a lot smaller. So we're seeing more lines and other just environmental lines in the system. The reason why they look less and less like a Lorentzian is because we are damping down for the lowest curve here. We've damped it to a Q of like around 2. So Lorentzian just becomes very flat.
The term is sort of like it's now just the Lorentzian is the same as mechanical oscillator response function in some calculation. By the same, I mean if I ignore the really low frequency part, here I'm basically seeing very damped mechanical.
Yes. Yes. So having used feedback for cooling, can we use it also for trapping? And why would you want to do that? Well, in gravitational wave detectors, they're very sensitive systems, but they don't yet have strong optical forces. So we want to use feedback to take their place, both of the restoring force as well as the damping force. And we know that feedback can approach the ground state for the case where the mechanical resonance falls within the cavity bandwidth, which is the case in which we're working. So we applied this to LIGO. All these tests were done at the Hanford 4-kilometer interferometer. So here we're dealing with 10-kilogram mirrors. The reduced mass of the 4 mirrors is about 2.5 kilograms, so 10 to the 26 atoms. And they're suspended initially. The resonant frequency is 0.7 hertz. So we used our servo spring to shift the resonant frequency out to about 140 hertz, and then also to damp, ultimately to a temperature as low as 1.4 microkelvin, which corresponds to occupation of only 234. And so that's a factor of about 200 million below where we started in terms of ambient room temperature. So again, you're seeing a heavily damped mechanical system down here. So in future gravitational wave detectors, we hope to closely approach the standard quantum limit. If we can do that, we can also approach the ground state by using this optimal feedback strategy of first shifting the oscillator to the frequency where we most closely approach the SQL. So in advanced LIGO, that'll be something below 100 hertz. And then subtract the energy from the oscillator using a cold damping force. And the resulting occupation number that you get depends on how closely your displacement sensitivity approaches the SQL. So if you can get within, in initial LIGO, we were within a factor of 10 of the SQL, or it's 100 in power, so we had about on the order of 100 quanta left. Okay, now I want to talk about some of the quantum aspects of radiation pressure and how we're looking for these things in our lab. So getting to the quantum regime in these systems is challenging. We've found it necessary to do the initial cavity locking at relatively low power because our system is so susceptible to radiation pressure forces, and they can be quite disruptive during our initial lock acquisition, where we're reducing the relative motion of the mirrors from something on the order of microns down to 1/10,000th of a micron, which is the size of our fringe. So after we've locked, we need to raise the input power by about 100-fold to as much as 5 watts while keeping the cavities locked. And this, as this is happening, the static radiation pressure force is displacing the mirrors by up to 1 millimeter while we're trying to maintain the relative position to within a 10,000th of a micron, and also while we're trying to maintain the cavity alignment, so we need to correct for the drift of both of these things. And very importantly, the quantum noise we're trying to see is the intensity noise of the differential mode of the two cavities, and that has to remain quantum limited, and that can be challenging because anything that couples to that intensity classically is going to scale with the power, and this is only going to scale with the square root of the power. So it gets harder and harder the more power you're trying to work with. So how are we doing? We can operate stably at an input power that's about 10% of the total that we have available, which is about 500 milliwatts. It's where we can operate. There's not really fundamental issues there, just dynamic range limits. We found it convenient to work here and try and get some of the technical noise down. And we're limited, we think, primarily by 2 different types of technical noise sources. At high frequency, we see thermal noise, which I'll explain in a moment, and at low frequency, we're seeing a scattering type noise. And at closest approach to our goal for a 5-watt input, we're within a factor of 3 or 4. So what's the technical noise coming from? Well, the low frequency limits we think is due to light that scatters out of a beam and then finds its way back into the system somehow. Scattered light creating these parasitic interferometers. So it's light that leaves and comes back, and the path length over that it travels is randomized, and so that adds noise to our measurements. And this cyan trace here is kind of showing an example of what you can get when you have scattered light. It's very characteristic shelf-like, step-like spectrum that can be 10 or 100 times worse than what we need. Sorry? To the scattered light, to the. Well, actually here you're probably seeing a scattering off of 3 or 4 different things. So if you only had one scatterer, you would see one step, and then so you see more than one. And the frequency and the amplitudes depending on how that scatterer is moving. Usually there's some characteristic speed in that. So we're trying to make the scattered light go away by first reducing the amount of scattering by using less imperfect optics, reduce the amount of motion by damping things that are moving, and using things like Faraday isolators and tweaking the alignment to take some of these problematic scattering paths and interrupt them, just break them. So we've got that more or less under control, and that's what lets us achieve the low frequency spectrum pretty consistently as we turn up the power. We don't see that change very much anymore. We used to see it change quite a bit. At higher frequency, we're limited by thermal noise in our system. So where's the thermal noise coming from? I told you about those ears that are supposed to prevent any bending of the fiber, and they do that because we get a Q of 10 to the 6 in the 10 hertz mode. So the fiber isn't bending where it shouldn't. But it turns out the ears themselves can pivot on the attachment point with mirror. And this is the type of bending that's limiting us right now. And the attachment is made with vaxial glue, and so it's lossy, and so those modes are very low Q, and we actually see the noise of those below resonance as a limit to our spectrum here. So we did a finite element analysis, and this is the culprit. So we can't very easily fix that without upgrading our suspensions, so we're working on that. We want to come up with a different form of attachment, or maybe even use the same form of attachment, but just make sure there's a lot of surface area here for the glue to bond to and not have a point contact, just to make that mode stiffer, or use a different type of glue. So in the meantime, while we're working on these suspensions, can we make any interesting measurements with the system we currently have? Well, several optomechanics groups have proposed using a correlation measurement because they're in somewhat the same situation. We already have a lot of thermal noise. The quantum signal you'd like to see is below the thermal noise. Can you pull it out with a correlation measurement? And the effect is also, I should say, been directly seen in an ultra-cold atomic system where thermal noise was not so much of an issue. So actually in LIGO, our colleagues who do data analysis use a very similar technique in order to access a different type of quantum fluctuations. Those quantum fluctuations I told you about at the beginning of the talk from the early universe are thought to be much weaker than anything that we could see with the current sensitivity we have in our detectors. And we still haven't seen anything, but we can put upper limits on how strong this stochastic background of gravitational waves can be by correlating the signals that we get from two different detectors. So we stick them into a correlation with some optimal filter that depends on the spectrum of the signal you're trying to see and the spectrum of the noise that you have in each of your detectors. And in order to make this work, you need the noises to be Gaussian and statistically independent. So we would like to do something very similar to this with our setup, where instead of quantum fluctuations of the early universe, we're looking for the intercavity powers quantum fluctuations, which will show up both in our mirror displacement, which is swamped by the thermal noise, and in vacuum fluctuations at the dark port, which we can monitor independently. So this is something we're currently trying to understand our noise and make this type of measurement work. Once we have seen the radiation pressure, and in fact once we've upgraded our suspension so we can see it directly, there's another effect we can look for, Ponderomotive squeezing. So here, this comes about because the radiation pressure is correlating the amplitude and phase quadratures. They're both correlated with the mirror motion. Amplitude is driving it, and phase is reading it out. So the amplitude quadrature, what comes out of the interferometer is the same as what goes in. The phase quadrature, what comes out is what goes in with the modification of the signal that is coming from the amplitude quadrature kicking the mirror around. So that means these two quadratures are correlated, which means there's some intermediate quadrature which is going to be squeezed, which is going to be below the noise of what you put in. So one of the things we've done is we made a noise budget to try and predict how much squeezing we could see in the system, which is taking into account the losses in the cavity and the laser noises and suspension and optic thermal noises. And we should be able to see up to 7 dB of squeezing in this system once we can see the radiation pressure at all. And this is an example of a system where we can take advantage of a stiff optical spring to both suppress some of the thermal noise and other technical noise sources that are trying to kick the mirrors around, and it also gives us a constant squeeze angle because of the way these quadratures are correlated, you would have a frequency-independent squeezing because of the free mass response. So if you use a stiff optical spring, then this becomes constant below the effective resonant frequency. And finally, if we go back to the trapping configuration where we're sending in two different colors of light, we can look for entanglement of those two fields, or a kind of joint squeezing of the fields that you send in. And this is really helping us to exploit the advantages of the optical trap configuration, which is stable at high powers and gives us strong coupling via the mirrors. The optical entanglement in this scenario is robust against the thermal noise, and that's what this plot is showing here. So this is logarithmic negativity plotted as a function of frequency for different environmental temperatures, and even at room temperature, there's a detectable amount left. And it could potentially be interesting for applications in a system like this, where you can any two wavelengths for which you can get good coatings for your mirrors, you can entangle them. So it can be useful for interfacing different. What is logarithmic negativity? This is a figure of merit for entanglement. It comes about from looking at the density matrix and whether when you apply a certain transpose operation to it, which is the equivalent of reversing time in one of the subsystems, whether you now have negative eigenvalues there. So that's something that classically you would never see, and quantum mechanically you can, and so that's giving you a signature of quantum entanglement. Okay, now to summarize, so I've told you about gravitational wave detectors and their quantum noise limits. They're getting close. The next generation of gravitational wave detectors should be limited mostly by quantum noise. I've described some classical radiation pressure forces and how they can dominate both trapping and cooling the mechanics. If future gravitational wave, or when future gravitational wave detectors reach the SQL, they will have a path to the ground state by feedback. And the regime of quantum backaction and squeezing and entanglement seems within reach in our system. I want to close by thanking my collaborators in Professor Nergis Mavavalla's group, Thomas Corbett, Tim Odia, Eric Olker, and Shannon Sankar, and LIGO lab members and the LIGO scientific collaboration. And thank you for your attention. Back to that. So, yeah, for example, so the way we measure the temperature of one of these modes is to integrate it using some finite band. You always have to use a finite band of integration so it doesn't diverge, and also because you're only sensitive to the mirror motion in some finite band. And then we compare it to what a Lorentzian. So we also integrate a Lorentzian over the same band. And set the integrals to be equal. So we find that the Lorentzian that would have the same integral has some temperature associated with it, and that's the temperature we associate with our system. Well, it is the range that I'm showing you. So that should always be an upper bound, right? Because you could be either seeing the motion of the system or you're seeing some sensing noise, which does not reflect what the system is actually in motion. So we define it in such a way that it's an upper bound.
Just subtract lots of value?
No, we don't subtract anything. We just integrate. That's because the shape of the underlying noise spectrum is, it has a dip there. So, in fact, you were probably not seeing the motion at all. I mean, whatever, the motion here is the motion that we're putting back onto the mirror by feedback. It's probably not thermally driven.
This is a measurement that's made in loop or using an independent?
This is made in loop, and we calibrate out the loop effects.
So to go to Dan's point, there's not squashing of the noise. In other words, not just creating anti-correlations in your feedback loop, which are suppressing the white noise. But presumably, you can make negative temperatures that way.
Yes.
So I will ask you, you've avoided the naive mistake of doing that.
We have avoided that, yes.
Okay.
So we don't know in our system whether each of these, whether at any given frequency, what we're seeing is limited by is a force noise or a sensing noise, basically. So we always choose the most pessimistic of those two, and that makes sure that we're not going to fool ourselves by creating a negative temperature.
But you don't have evidence measuring
Yeah, that would be a bigger modification than they would let us make to LIGO. Well, I think I put one number up at the very beginning, and I should have called it out. So the level of strain that we're trying to detect is on the order of 10 to the minus 21. And, so we haven't detected a signal yet. This is what the theorists tell us we should expect. And we haven't seen it yet. We have built detectors that are sort of comparable to this in sensitivity, and the next generation of detectors is going to take us another order of magnitude down. So the expected rates in that case are going to be at least like a few in a month, as opposed to so far none in about a year of continuous running at the best sensitivity.
So am I correct in believing, speaking without being recognized by Dan, until he irritated him, just is it true that there is some sort of neutron binary that if you had a better sensitivity, you should just be able to go and find that it's there, and what sensitivity would you have to reach to see that signal?
Well, there is an example of a system. I mean, this is the indirect detection of gravitational waves that was done in 1993 that won the Nobel Prize,
Sure.
where that's a very low frequency system, unfortunately, at this point in its evolution. But we know that the evolution of that system is consistent with it emitting gravitational waves.
Yeah, but if you lock your gravity wave detector to that particular frequency, could you integrate for a week and decide that you could pick out that peak?
I think it would take a lot longer than a week.
Okay.
100 years from now, that particular system will be in our band.
So it's really just way too low frequency wave?
I think it's 8 hours, isn't it?
8 hours? I see.
Yeah.
Okay.
Yeah.
These bounces are actually millimeters.
Yes. Yeah. Less than that.